from us, the light waves are stretched out. They drop in frequency and shift toward the red end of the spectrum, which is naturally a redshift.
So we aren't looking for the star to physically sway back and forth in the sky. We are watching it rhythmically change color.
Exactly. We point massive, ground-based spectrographs at the star and look for its light to shift from slightly blue to slightly red and back again on a predictable, continuous loop.
And the timing of that rhythmic color shift tells us the orbital period of the planet, right? Because it takes one complete orbit of the planet to pull the star through one complete wobble.
That's right. But the critical piece of new data we gain here is from the amplitude of the shift.
The amplitude.
Yes. How severe is the blue shift? Basically, how fast is the star being yanked toward us?
Because a more massive planet has a stronger gravitational pull, so it will yank the star with more force.
Exactly. A stronger pull causes a faster wobble, which creates a more dramatic Doppler shift. So the radial velocity method allows us to calculate the planet's mass, specifically its minimum mass.
That's incredible. We are effectively weighing a world we cannot even see just by measuring how much it throws its star off balance.
It is a profound piece of deductive reasoning.
Let's synthesize these two methods for you listening at home, because this is where the science transitions from abstract data points into tangible, actual world building.
It really is the magic combination.
The transit method gives us the planet's physical size, its volume. The radial velocity method gives us the planet's mass.
Right.
So when we find a planet that randomly transits, and we also manage to measure its Doppler wobble, we suddenly have both the volume and the mass of the same planet.
And dividing the mass by the volume yields the planet's density.
Density.
And density is the master key to understanding what a planet is actually made of.
Right, because knowing a planet is twice the size of Earth is interesting, but knowing its density tells us if it's a place we could theoretically stand on.
Exactly. A high density indicates a tightly packed, rocky composition with a solid surface, analogous to Earth or Mars or Venus.
A rock.
A rock. But a low density, despite having a large mass, indicates the planet is mostly composed of light gases. So it would be a bloated, puffy world, more like Saturn or Neptune.
So calculating density allows us to draw the boundary lines between what astronomers call super-Earths and mini-Neptunes.
Yes, it separates the rocky globes from the swirling gas clouds.
Now, both of these methods, transit and radial velocity, they're incredibly elegant, but they are entirely indirect.
They are.
We are inferring the existence and the properties of the planet based purely on how it terrorizes its host star, either by blocking its light or pulling on it gravitationally.
Right, the star is our only direct informant.
But human nature kind of dictates that we eventually want to just look through a lens and see the thing itself. So the obvious question from the source material is, can we take a direct photograph of an exoplanet?
We can through a method called direct imaging. But as the source material heavily highlights, it is the most extreme engineering challenge in modern astronomy.
Because we immediately crash back into the searchlight and the firefly problem we talked about at the start.
Exactly. The star's glare will obliterate any direct optical image of a planet orbiting anywhere near it.
So to take a picture, we basically have to invent a way to turn off the searchlight without turning off the firefly.
Which sounds impossible, but the mechanical solution is an instrument called a coronagraph.
A coronagraph.
It is a highly engineered, microscopic physical mask placed perfectly inside the optical path of the telescope itself.
And the sources describe it beautifully, like the sun visor in your car. When the blinding sun is directly in your eyes while you're driving, you pull down the visor to physically block the direct disk of the sun.
Right.
And suddenly, the glare is reduced enough that you can actually see the road and the cars around you again.
A coronagraph does exactly that on a telescopic level. It acts as an opaque disk that literally eclipses the primary star within the telescope.
So it creates an artificial eclipse inside the machine.
Exactly.
Yeah.
It blocks the overwhelming photons of the host star while allowing the incredibly faint photons from the surrounding space, where the planets are, to slip past the mask and hit the camera sensors.
Okay, but if you are using a ground-based observatory to do this, you are looking up through Earth's atmosphere, and our atmosphere is constantly boiling and churning.
It is. It's very turbulent.
It's what makes stars twinkle to the naked eye, right?
Yes, that twinkle is atmospheric distortion.
So if you are trying to block a microscopic point of light with a tiny physical mask inside a telescope, Even a tiny bit of that atmospheric shimmer will blur the star's light right past the edge of the mask and completely ruin the image.
Which is a massive hurdle. And it's why direct imaging on Earth requires a secondary, highly advanced technology known as adaptive optics.
Adaptive optics.
To neutralize that atmospheric distortion, observatories actually fire powerful lasers up into the upper atmosphere to create an artificial guide star.
Wait, they shoot lasers into the sky?
Yes. Computers then analyze exactly how the turbulent atmosphere is blurring that specific laser light on its way back down.
And they use that data to fix the blur in real time.
That's the crazy part, yes. They feed that distortion data into a deformable mirror situated behind the telescope lens.
A deformable mirror.
It's a mirror that has hundreds or even thousands of tiny computer-controlled actuators behind it. They are physically pushing and pulling the surface of the glass thousands of times a second to perfectly counteract the atmospheric turbulence as it happens.
That is insane.
It flattens the light waves out, creating an image that is almost as crisp as if the telescope were floating out in the vacuum of space.
Okay, so we have a coronagraph visor blocking the glare, and adaptive optics mirrors aggressively smoothing out the twinkle. But even with this incredible sci-fi setup, we still can't just point it at an Earth-like planet and snap a quick photo, can we?
No, unfortunately not. Direct imaging is a highly selective tool. It completely fails for small, rocky planets, or even for older, larger planets sitting close to their stars,
Why is that?
because the physics of contrast still rule the day. To successfully capture a direct image, we need an incredibly specific target profile.
Okay, what does the perfect target look like?
The planet has to be massive. Think Jupiter size or much larger, so it has a large reflective surface area.
Okay, big.
It also must orbit extremely far away from its host star. This ensures it is physically separated from the residual glare that still spills around the edges of the coronagraph mask.
Big and far away.
But the most fascinating requirement to me is that the planet must be very young.
Young. Why does the age of the solar system matter for taking a photograph?
Because a young planet is a hot planet. When planets form, gravity violently crushes immense amounts of gas and dust together.
Right, planetary accretion.
And that gravitational collapse generates terrifying amounts of internal heat. For the first few million years of a planet's life, it doesn't just reflect starlight passively, it aggressively radiates its own internal thermal energy out into the void.
Oh, so it glows.
Exactly. It glows very brightly in the infrared spectrum. So by outfitting our telescopes with infrared sensors, we aren't just looking for a cold rock reflecting a sun, we are actively seeking the heat signature of a newly forged world glowing in the dark.
That makes a lot of sense.
In infrared, the brightness gap between the star and the planet narrows significantly, making the planet much easier to spot.
Now, when all of this actually works, the coronagraph, the adaptive optics lasers, the infrared sensors, and we finally capture that image, I want to make sure you, the listener, have the right visual in your mind.
It's important to set expectations, yes.
This is not a National Geographic centerfold. We are not seeing continents or oceans or swirling atmospheric bands like you see in pictures of Jupiter.
No, the final data product is incredibly stark. It is really just a tiny, pixelated dot of light sitting in an expanse of blackness, positioned near a dark, artificially masked out circle where the host star was eclipsed.
It is essentially just a smudge.
It is a smudge.
But the philosophical weight of that smudge is just unbelievable. I mean,
Sure.
think about it. That single pixelated dot is actual literal light generated by an alien world trillions of miles away. It traveled through the vacuum of space for years, slipped past a physical mask, bounced off a shape-shifting mirror, and was recorded by a camera built by human beings. It is an astonishing technological triumph.
It truly is. And when you step back and evaluate these three core methodologies, transit, radio velocity, and direct imaging, you see that none of them provides a complete picture in isolation.
Right, they all have their blind spots.
Exactly. Modern planetary science relies on them as complementary pieces of a much larger cosmic puzzle.
We use the shadow from the transit method to measure its physical size. We use the gravitational wobble of the radial velocity method to weigh its mass and determine its density.
Yeah.
We use transmission spectroscopy to dissect the chemical makeup of its sky. And in rare specific cases, we use direct imaging to capture its actual thermal glow.
By combining these disparate, highly specialized data streams, we construct remarkably detailed profiles of planets that we will never, ever physically visit.
The speed at which this field has advanced is just dizzying to me. If we rewind to the early 1990s, The number of confirmed exoplanets was 0.
Zero. We have theories, sure, but absolutely no proof.
And in a single human generation, we have gone from 0 to thousands of confirmed worlds, with the statistical certainty now that billions more populate our galaxy alone.
And honestly, the most shocking outcome of this planetary census isn't just the sheer volume of worlds we're finding, it's their extreme diversity.
Right, they aren't all just copies of Earth and Mars.
Not at all. The systems we are discovering do not look like our solar system. The universe is incredibly creative, and the exoplanet zoo we've cataloged challenges everything we thought we knew about planetary formation.
We are finding worlds that completely defy the imagination. The sources highlight ocean worlds, where the entire surface is submerged under global abyssal seas with no land in sight.
Yes, or we found lava worlds orbiting so punishingly close to their stars that an entire hemisphere is just a permanent, roiling ocean of molten magma.
And didn't we find planets where it rains gems?
Oh, yes. We've identified massive gas giants with internal atmospheric pressures so extreme that carbon is crushed into diamonds, causing literal diamond rain to fall toward their cores.
Diamond rain. That is just, it's so sci-fi, but it's real.
Mhm.
Yet driving all of this, the ultimate holy grail of exoplanet research remains the search for Earth 2.0, right?
Always. A quiet, rocky planet sitting right in the habitable zone of a stable star with an atmosphere capable of supporting liquid water.
Finding that specific combination of traits requires pushing our current technology to its absolute limits. But the philosophical shift is palpable in the source material.
It is. The scientific community no longer views the discovery of a truly habitable Earth analog as a question of if.
Right.
It is merely a question of when we will find it.
Which brings me to a final thought I want to leave you with. Something to mull over that builds on everything we've talked about today. Think about this. The source notes that our galaxy alone is estimated to hold billions of planets. And we've already found lava worlds and gas giants raining diamonds just by looking at our tiny, immediate cosmic neighborhood.
Just scratching the surface.
Exactly. If we found things that bizarre so quickly, what completely unimaginable, physics-defying worlds are still waiting out there in the dark, with billions of rolls of the cosmic dice? Is it possible that a quiet, rocky Earth is actually the weirdest type of planet out there?
That is exactly the kind of question that keeps us pushing the boundaries of what our telescopes can see. It's a vast universe.
It really is. Well, thank you so much for joining us for this deep dive. If you loved unpacking the ingenious methods we use to hunt for alien worlds, please make sure to follow or subscribe. Leave us a 5-star review on your platform of choice and share this deep dive with a fellow space nerd. Until next time, keep your eyes on the skies and keep wondering.